Hi everyone. Before we get started, I just have a couple of quick announcements. First thing is that I posted the final review on Canvas, so please go look at that. And I'm going to be making a video probably on Friday where I go over some questions from the review. So there's a survey that I also put on Canvas where you can just go and check off any questions that you specifically or especially want me to go over from the review. So it'd be great if you could do that before Friday so that I can make a video that is most helpful to people in the class. I'll post solutions soon. I'm working on them. I'll probably get them up sometime tomorrow. I'm recording this on Tuesday night. So when I say tomorrow, I mean Wednesday, but for you, that might be today. Anyway. I also sent out an email with a bunch of information about how the final exam is going to go. So please read through that and make sure everything makes sense to you. And if you have any issues or questions, concerns, anything, just let me know right away because I really want to resolve any issues that might arise with the final before the actual final time. Okay, so we are going to pick up where we left off last time. So today and tomorrow's videos are going to be the last two kind of new topic videos, and these are both going to be about what's called diagonalization. Diagonalization. So I'm going to start by recapping something we talked about at the end of yesterday's lecture, and then we'll transition into diagonalization. So yesterday we talked about the fact that a matrix A is called similar to a matrix B if you can write A as P, B, P inverse for some invertible matrix P. So I'm going to write down a couple of examples of this. One is from yesterday's worksheet and one is from yesterday's video. So the example from the worksheet was the matrix 2, 3, 3, negative 6 can be written as 3, 2, 1, 1 times 15, 8, negative 33, negative 19 times 1, negative 1, negative 2, 3. So in this example that I just wrote out here, so this is our matrix A, this is our matrix B, and then we have P and P inverse. And so in this case, we would say that A is similar to B. So this is one kind of example of, one example of two matrices that are similar. However, in this section, we're going to be seeing a specific type of similarity. So I'm going to write down one other example that came from yesterday's video. And so that was the example where the matrix 2, 7, 7, 2 could be written as 1, 1, negative 1, 1 times, 9, 0, 0, negative 5 times 1/2, 1/2, negative 1/2, 1/2. So I'm going to label this one as well. So I'm going to call, instead of calling it B, I'm going to actually call it D, and we'll see why that is in a minute. And so in this case, this is P and P inverse. And so in this case, we would say that the matrix A is similar to D. Okay, so this second example that we're talking about is the type of example that we'll be looking at in this section. So why did I use the letter D here? It's because the second matrix is a diagonal matrix. So a diagonal matrix meaning that the only entries are on the main diagonal. So the main diagonal goes from top left to bottom right. So if you have a situation like this, then you can call the matrix A, the matrix that we started with, a diagonalizable matrix. So a matrix A is called diagonalizable. And so diagonalizing is the process of figuring out how to write it the way that we did in this previous example. And that's what we'll be talking about in this section. But a matrix A is called diagonalizable if it is similar to a diagonal matrix, specifically D. In other words, if you can write it as A is equal to P times D times P inverse for some diagonal matrix D and invertible matrix P. So for example, the matrix A from above is a diagonalizable matrix. So let's write that down here. So the A that we had above is called a diagonalizable matrix. So we'll get into in a little bit how you actually come up with this kind of diagonalization. You know, so far, like I just told you that this was true, and you can check that it is by multiplying it, but today we'll talk about how, how you could actually figure that out yourself. But before we get there, I just want to remind you, why does this matter? Like, why would you try to diagonalize something? And so let's see, how far have we gone on this page? Let me go to another page. Actually, I'll stay on this page. So when I export these, if I go too far onto the page, when I export the lecture notes, it gets cut off in strange places, but I don't think this is yet to that length, so hopefully I'm right about that. Okay, so why is diagonalization useful? So this is something you actually already explored on a written homework a while back. So at least one of the reasons that diagonalization is useful is because it allows you to evaluate powers of a matrix more easily. So, for example, or in general, if A is equal to P times B times D times P inverse, then taking that matrix and raising it to some power K is the same thing as doing P, D, P inverse to the K. And what does it mean to take something and raise it to the K power? Well, it means you're multiplying it with itself K times. So you have to be careful here because when you're multiplying matrices, you can't just kind of swap around the order. But I'm just going to start writing out a few examples here, and then you're doing a bunch of multiplication in the middle, and then maybe at the end you have a couple. So let's say you did this K times, right? That would, if you're raising it to the power of K, that means you're multiplying it with itself K times. And so what happens here, well, if you look at the how things get kind of smushed together, you end up with a P inverse times a P here. You end up with that's going to happen again here, that's going to happen again here, it's going to happen everywhere in the middle, it's going to happen here. And so anytime you have P inverse times P, that's always going to equal the identity. And so it's basically just going to go away. And so what are you going to be left with? You're going to be left with just just one P from the beginning, and then you'll have K Ds being multiplied together, and then you'll have P inverse. And so the nice thing about this is, so as you saw on that homework assignment, when you have a diagonal matrix, it's really easy to raise it to a power. So for most matrices, to multiply, like if you took a random matrix, like let's say this one A by itself, if you try to take this matrix A and multiply it with itself, let's say like 5 times, you can't just raise every entry to the 5th power, right? That would not give you the right matrix. You would have to actually do a bunch of work and do a bunch of multiplication. With a diagonal matrix though, to raise it to a power, the way that the multiplication works out, it's the same as just raising each entry to that power. And so maybe I'll make a note of that. This is easy to do. So basically what happens is you end up, like, let's say you're raising it to like the 5th power. Originally you would have to multiply a matrix with itself 5 times. If you use the diagonalized version, well then you're just multiplying actually 3 matrices together, because the 5th power part you can do very efficiently. And so if you think about, real world examples, there might be examples where you have to raise a matrix to like the 100th power, something like that. And it's going to be a lot less computationally intensive to approach it in this method than to just take the matrix and kind of multiply it by itself. So maybe just to quickly write out an example without fully doing it. But like if you were trying to raise, let's say 2, 7, oops, wrong matrix, 7, 2, let's say you wanted to raise that matrix to the 10th power. Well, instead of having to do 10 matrix multiplications, what this allows you to do instead is you would just multiply, so this is our matrix P, then you would have the matrix in the middle, that would be, so the diagonal matrix that we had, you would just raise each of those entries to the 10th. And then you would have your inverse matrix. So, we don't actually have to go and do this out because the numbers are going to be huge, but at least you're hopefully convinced that it's less work than having to multiply 10 matrices together. So that's some kind of background motivation you can think about, like when we're doing this, of like why you would ever do this. Okay, so it turns out that not every matrix is diagonalizable. And so what I want to do next is kind of tell you what the condition is that allows something to be diagonalizable. And then we'll see that there's directly connected to that condition is a way to actually come up with the diagonalization. So in your book, this is called the Diagonalization Theorem. So basically it says a matrix A, sorry, I should say, get a little more specific here. So an n by n matrix A is diagonalizable if and only if, so that's what this double arrow thing means, that matrix A has n linearly independent eigenvectors. So, we've talked about how to find eigenvectors, and basically if those eigenvectors you find, if you take all of them and you have n of them and they're all linearly independent, then that will mean that the matrix is diagonalizable. And so if this is the case, maybe let me switch colors. So if A is diagonalizable, then specifically you can write it as, like we said earlier, P times D times P inverse, where the matrix P is going to consist of the columns of that matrix are going to be your linearly independent eigenvectors. So you'd have n of them. And so remember that the matrix P is supposed to be invertible. So it is, right? If we already said that the eigenvectors have to be linearly independent. So maybe let me even I can add that to our definition here. So we're calling V1, V2, Vn. Those are representing the linearly independent eigenvectors. So this matrix P has linearly independent columns, therefore it's invertible. And then what is the matrix D? Well, D is going to be, as we saw actually in that last example, I'll go back to it in a second, D is going to be a diagonal matrix where the entries on the diagonal are the eigenvalues that correspond to these eigenvectors. So lambda 1, lambda 2, dot, 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 lambda n. And so you might have some repeated eigenvalues, and we'll see an example like that actually shortly. So the eigenvalues don't all have to be different, but you do need to have like the eigenvalues and eigenvectors that go together matched up. So we'll see that in a second. I'm just going to write a big 0 here and here to represent that all the other entries are zeros because it's a diagonal matrix. So let me just write that last thing I said, which is that lambda 1, lambda 2, lambda n are the eigenvalues corresponding to the eigenvectors v1, v2. So like I said a moment ago, you can have one eigenvalue that has multiple eigenvectors with it. And we'll see an example like that in a minute, but if you think back to when we first started talking about finding eigenvalues and eigenvectors, we found ones where like the set of all eigenvectors was the span of two different vectors. So you could definitely pick two different vectors, two linearly independent different vectors to be the eigenvectors. And then the eigenvalue would just be the same for those two different eigenvectors. So just give one quick example, again, just going back to the example we already did. So the matrix 2, 7, 7, 2, we actually did this example, I can't remember if it was on, I think it might have been on the worksheet when you did eigenvalues and eigenvectors. So this matrix has eigenvalues lambda 1 is equal to 9, and lambda 2 is equal to -5, and then the eigenvectors are v1 is equal to 1, 1, and v2 is equal to -1, 1. And so when we wrote out that diagonalization, we ended up with that matrix P. Let me mix things up with some color here. So let's do. So our matrix P was 1, 1, -1, 1. And so those two columns came from these two eigenvectors. And then the middle, the diagonal matrix, had our two eigenvalues. So it was 9, 0, 0, -5. And then you would have to then find the inverse of P in order to finish this off. So the last matrix is the inverse of P, which is this. So, by the way, tomorrow's video, I'll kind of go through like a proof of why this works, but for today, I just wanted to do some examples so that you can get familiar with the process of doing it, and then tomorrow we'll get more into like the theory of why it works and some kind of like special cases. Okay, so let's do a couple of fresh examples now that we've really exhausted this one. One other thing I should say is that it doesn't matter the order that you kind of put the different eigenvalues and eigenvectors as long as they're in like the corresponding order. So there are multiple ways to diagonalize a matrix, but you just have to be consistent. So, if I had switched -5 and 9 in this case, I would also have to switch these two columns in order to make it work, and then that would also change the inverse. Okay, so let's do a couple of examples. So we're going to find a diagonalization for the following matrix: 1, -3, 3, 3, -5, 3, 3, -3, 1. If possible. So we're going to do two different examples. One we'll see is diagonalizable, and another one we'll see is not. So we'll get to see what it looks like when it's not. Okay, so as we saw in the last chapter, so when I gave you examples of matrices and asked you to find the eigenvalues from scratch, if they were 3 by 3, they were usually pretty sparse, right? They would be like matrices where almost everything's a 0, because otherwise it's just really kind of a pain to come up with the characteristic polynomial and find the eigenvalues. So in this case, I'm actually just going to tell you what the eigenvalues are, and that's what it will probably be like in this section. If it's like a very simple matrix, maybe you'll have to find them yourself, but there might also be examples where it's just like, I'm just going to tell you what the eigenvalues are. So the eigenvalues for this one are, so eigenvalues, and I'll just write down, these are given. So one of them is lambda equals 1. And that has, by the way, we want to keep track of the multiplicity. So that's how many times, if you were to write out the characteristic polynomial, how many times that the factor corresponding to that appears. So that has multiplicity 1, and then the other eigenvalue in this case is -2, and that one actually has multiplicity 2. Okay, so those are the eigenvalues. And then the eigenvectors, so I'm just going to tell you these, but you could actually, whereas coming up with the eigenvalues in this case would be a little bit tricky, you totally know how to come up with the eigenvectors. So basically, how would you do this? You would, if you wanted to find these, you would solve sorry, let me put that differently. You would solve the determinant of A minus lambda I times x is equal to 0 for lambda is equal to 1 and lambda is equal to -2. So the eigenvectors that we get are, so if you were to do 1 as your eigenvalue, you would just get the eigenvector 1, -1, 1. So this one goes with lambda equals 1. And then if you were to do lambda equals -2, this one you would get 2 different eigenvectors. So this is like, we did some examples like this where when you solve, you end up with the span of 2 different vectors. And so you can pick out 2 different vectors that are linearly independent from one another. So we can kind of choose, but let's just say, that lambda 1 is equal to 1. And then I'm actually going to call the other eigenvalues lambda 2 and lambda 3, even though they're the same one, just to be consistent with our numbering system. I'm going to write it twice. And then the corresponding eigenvectors are going to be v1 is, I should have spaced this out a little bit more, but that's okay, 1, negative 1, 1. The second one is going to be negative 1, 1, 0. And then the third one is going to be negative 1, 0, 1. So these are our three eigenvectors. And so before moving on to finding the diagonalization, we want to confirm that it is actually diagonalizable. So remember that the condition that we're looking to meet is that we have to have three linearly independent eigenvectors. And in this case, we do. It's not too hard to kind of tell just by looking at them, but you could also, make a matrix and reduce it, and you would find that these three eigenvectors are linearly independent. And so this tells us that our matrix can be diagonalized as follows. So let me use a different color. So if you wanted to diagonalize this, you could write it as, so our matrix P is going to have the three vectors that we just came up with as the columns in the order that they're written. So that's our matrix. This is our P. And then the diagonal matrix is going to have the eigenvalues 1, negative 2, and negative 2 as its diagonal entries. So this is our D. And then, I didn't write down P inverse. I meant to do that ahead of time, but let's do it ourselves. So I was going to tell you in the video that you should try it yourself, but then I was going to come in with the answer, but I didn't do that ahead of time. So let's go off to the side and do that. So how do we find P inverse? This is good review of this process. Basically, you want to take your matrix P and adjoin it with an identity matrix. And so what we're going to do is we're going to do row operations to reduce the left side to the identity, and then whatever we're left with on the right side is going to be our inverse. Okay, so let's see, this shouldn't be too bad because we have a lot of ones and zeros, or only ones and zeros basically. So let's do, let's add one copy of row 1 to the second row and subtract one copy of row 1 from the third row. So that should leave us with, so on the top we'll still have 1, negative 1, negative 1, 1, 0, 0. So the second row we should get 0, 0, negative 1, and then 1, 1, 0. And then our bottom row, so we're subtracting row 1, so we're going to get a 0 in the first entry, and then a positive 1, and then a 2. Is that right? Yeah. And then on the bottom row, we're going to have, so we're subtracting the first row, so that's going to be like that. All right, maybe let's swap. It doesn't really matter. But yeah, let's swap these two rows. I think that's probably the best. So that would be 0, 1, 2, 0, 0. And maybe let's, well, I'll write it like this first and then I'll just change it. But we can flip the sign of that negative 1. So this is going to give us now, top row is still 1, 0, 0. Now we're going to have negative 1, 0, 1, and then 1, 1, 0. Hopefully I'm not making mistakes in this. Okay, so maybe let's, before we negate things, let's just add, so if we add 2 copies of the third row to the next row up, then that will clear out that 2. So we'll have 1, negative 1, negative 1, 0, 1, 0, 0, 0, negative 1. And then when we do that adding of the third row, that is going to change our second row. So we're going to have 2, so that will make a positive 1, a 2, a 1. All right, we're getting there. Then we can add, so we want to actually subtract 1 copy of row 3, and then we're also going to add 1 copy of row 2 to our first row. That should really kind of do it. Obviously, you can feel free to fast forward through this if this is boring. So let's see, that's going to give us so minus, let me just write this out first. Okay, so if we're subtracting row 3, so that's going to give us I'm going to write like a temporary thing here, so that's going to give us 0, and then we're going to get -1, and then this is still 0, so that's just subtracting row 3 from the first row. But then we're also going to add row 2 to that, so I'm going to redo this. So adding row 2 will then give us 1, and then this will become 1, and then this will also become 1. And then the only thing we have to do is multiply that bottom row by -1, and so that will give us 1, 0, 0, 0, 1, 0, 0, 0, -1. And probably should have just paused the video and looked this up. That's okay. Too late now. Okay, so we found our inverse. So the inverse is going to be 1, 1, 1, 1, 2, 1, -1, -1, 0. Let's see if I can remember that. Nope. Okay, so first column 1, 1, -1. Second column 1, 2, -1. And then I believe the last row was 1, 1, 0, but let me just double check that. Yes. Okay, so there's our P inverse. Sorry about that. Okay, so that's it. That is how you diagonalize a matrix. And so one thing I just want to quickly mention, if you wanted to check this, so obviously one way that you could check it is you could multiply these 3 matrices back together, and you should get the same matrix that you started with if everything went correctly. However, that's not really something you probably want to do. That's a lot of matrix multiplication. One thing that your book suggests, which actually, I guess actually this, so the reason your book suggests this is because in your book, when they do this problem, they actually don't compute P inverse, because they say, well, we've shown that it can be diagonalized. We don't need to actually write out what P inverse is. And so the way that your book suggests that you can check this, the reason that they suggest that you can check it this way is that you don't need to know P inverse in order to check this. So you can you kind of have 2 choices. You can either check that does A equal P, D, P inverse. That's kind of the more obvious check. But an equivalent way of checking that is you could check, so if you took this equation that I just wrote next to number 1, if you multiply both sides of that by P on the right, you would get AP equal to PD. So if you don't feel like computing the inverse, but you want to check whether you did this correctly, you can check whether your original matrix multiplied with the matrix P gives you the same thing as multiplying P with D. So I just wanted to let you know about that option. Okay, so let's do one more example together. So let's say we wanted to, again, we're going to find a diagonalization. And again, I'll write, if possible, of the following matrix. So this one is 2, -4, 3, 4, -6, 3, and 3, -3, 1. So again, in this case, I'm just going to tell you what the eigenvalues are, because the characteristic equation would be kind of a pain to come up with. So the eigenvalues are 1 and -2 again, actually. So it's the same eigenvalues, but we'll see the eigenvectors are a little different. Sorry, I forgot to write the multiplicity. So multiplicity is the same as well. So the first one is multiplicity 1, and then the second one is multiplicity 2. So if you were to go through finding the eigenvectors for this one, so same approach that we mentioned in the last one, which was solving A minus lambda I, or the determinant of A minus lambda I equals 0. And I just realized I think I wrote something wrong on one of these. I feel like I wrote something weird. Oops, yeah. Sorry about that. So going back to quite a while ago, so I just kind of mixed up two things when I wrote this down. So earlier when I wrote down how to find the eigenvectors, I wrote something kind of weird. What I should have written, so let me just cross this out. What I should have written instead was that you're just trying to solve the determinant, or sorry, you're trying to solve A minus lambda I times x is equal to 0. So what I wrote down, so I started to write down determinant of A minus lambda I because that's how you find the actual eigenvalues. Once you have the eigenvalues, you find the eigenvectors just by doing A minus lambda I times x is equal to 0. So sorry about that. But let's get back to this. So the eigenvectors, in this case, if you were to do that same process, you would get that there's only one eigenvector for lambda is equal to 1, and then additionally, there would only be one eigenvector for lambda is equal to 2, or -2. So in this case, what's the problem? We don't have n, so this is a 3 by 3 matrix. We would need there to be 3 linearly independent vectors, eigenvectors, in order for this to work. But what we ended up seeing is that there are not 3 linearly independent eigenvectors. So the matrix A is not diagonalizable. Cool. So I think that's it for today. I will, like I said, I'll post a worksheet that just has a couple of examples of this stuff, and then tomorrow we'll get more into a little more of like the theory behind this stuff, and yeah, that's basically it. And that will be our last topic for the quarter, is diagonalizing matrices. So thank you for watching, and I will